There are more stars in the universe than grains of sand on every beach on Earth. An estimated 200 billion trillion stars scattered across observable space, each one a sun, many hosting planets. Some of those planets potentially harboring life we'll never know about because their light hasn't reached us yet and never will. The universe expanding faster than light can travel across the distances separating us. Right now, as you listen to this, you're moving through space at over 1.3 million miles per hour. Not just Earth's rotation or orbit around the sun, but our solar system's movement through the galaxy's movement through its local group, the local group's movement through the universe's large-scale structure, all of it carrying you on a journey through the cosmos at speeds that would cross the continental United States in less than 3 seconds. The atoms in your body were forged inside dying stars billions of years ago. You are literally made of stardust. Every calcium atom in your bones, every iron atom in your blood, every carbon atom in your cells was created in stellar furnaces that exploded long before Earth existed, scattering their elemental gifts across space where they eventually coalesced into you. And here's what almost nobody realizes. Space isn't empty. It's seething with quantum fluctuations, with particles popping into and out of existence, with dark energy pushing the universe apart, with gravitational waves rippling through the fabric of space-time itself, making what looks like nothing actually something far stranger than we have words to describe. But let me start from the beginning. Welcome. I'm glad you're here. This is a space for calm exploration, where we examine the infinite through the lens of wonder rather than fear, where we discover that the universe, for all its vastness and strangeness, connects intimately to the very small scale of human life. If you're new here, this channel is dedicated to exploring the cosmos and its mysteries in a way that soothes rather than overwhelms, that makes the incomprehensible feel like a gentle companion to rest. If you'd like to join us for more journeys like this one, I'd be grateful if you'd subscribe and turn on notifications. Your presence here means everything. Tonight, we're going to explore space, not the sterile vacuum of science fiction or the mathematical abstraction of physics textbooks, but the actual physical reality beyond Earth's atmosphere, the place where stars are born and die, where planets form and evolve, where galaxies collide across billions of years, and where the fundamental nature of existence reveals itself in ways that challenge everything we think we understand about reality. This isn't about memorizing facts or understanding equations. It's about standing at the edge of human knowledge and feeling simultaneously small and connected, insignificant and essential, temporary and eternal. Settle in. Let the world around you fade, and let's discover together what the universe reveals about existence itself. When you look at the night sky, you're looking backward in time. Light travels at 186,282 miles per second, fast enough to circle Earth 7 times in a single second. Yet space is so vast that light from distant objects takes years, centuries, millennia to reach us. The light entering your eyes from the nearest star, Proxima Centauri, left that star 4.24 years ago. When you see it, you're seeing what it looked like when that light began its journey, not what it looks like now. The Andromeda Galaxy, visible as a faint smudge in dark skies, appears as it was 2.5 million years ago, before humans existed, before the most recent ice age, when our ancestors were still early hominids in Africa. Some objects we observe through telescopes are so distant their light has traveled for billions of years, showing us the universe as it existed when it was young, when the first stars were forming, before Earth was born. This means astronomy is archaeology. We study the past, not the present, reconstructing cosmic history from ancient light that has journeyed across unimaginable distances to reach our instruments. We can never see the universe as it is now, only as it was. And this connects to something remarkable about cosmic distance. Space is so vast that normal measurements become meaningless. Astronomers use light years. The distance light travels in 1 year, about 5.88 trillion miles. But even this unit becomes unwieldy quickly. The observable universe extends approximately 46.5 billion light years in every direction, creating a sphere of observability 93 billion light years across. Beyond this horizon, light hasn't had time since the Big Bang to reach us. There could be infinite space beyond what we can see, possibly containing infinite galaxies, infinite stars, infinite possibilities, but we're causally disconnected from it, existing in cosmic isolation where we can observe only our local bubble of space-time. The observable universe contains an estimated 2 trillion galaxies, each containing millions to trillions of stars, creating numbers so large they lose meaning. Trying to comprehend the universe's scale is like an ant trying to understand human civilization. The gap between our experience and cosmic reality, too vast to bridge intuitively. We grasp it mathematically, but not emotionally, understanding the numbers without feeling their weight, which brings us to understand what space actually is. Space isn't simply emptiness. It's a physical thing, a fabric that can bend, stretch, and ripple. Einstein's general relativity revealed that mass and energy curve space-time, creating what we experience as gravity. Massive objects, like stars and planets, create wells in space-time's fabric, and other objects moving through this curved space follow paths we perceive as orbits or trajectories. The fabric can be compressed, stretched, and even torn under extreme conditions. Black holes represent space-time curved so severely that nothing, not even light, can escape beyond a certain boundary called the event horizon. The universe's expansion isn't objects moving through space, but space itself expanding, carrying galaxies apart like dots on an inflating balloon. This means space has properties. It can be measured, manipulated, and studied. It's not passive background, but active participant in cosmic events, responding to mass and energy, while simultaneously defining how matter and energy behave. The universe is thus a dynamic, evolving entity rather than static stage. But there's more to this story of emptiness. Even in the deepest vacuum of intergalactic space, far from any star or galaxy, space is not truly empty. Quantum field theory predicts that what we call empty space is actually filled with quantum fields, invisible substrates permeating all of reality. These fields constantly fluctuate, creating virtual particle-antiparticle pairs that pop into existence and annihilate within fractions of a second, never lasting long enough to be directly observed, but leaving measurable effects. The Casimir effect demonstrates this. Two uncharged metal plates placed extremely close together in vacuum experience, an attractive force because the quantum fluctuations between the plates differ from those outside, creating measurable pressure differential. Empty space also contains dark energy, a mysterious force causing the universe's expansion to accelerate. Dark energy comprises approximately 68% of the universe's total energy, yet we don't know what it is, just that it exists, that it's pushing space-time apart, and that it will ultimately determine the universe's fate. Space is thus crowded, with invisible phenomena, bustling with activity we can't see, full of things we detect only through their effects on matter and light. And this leads to something equally fascinating about cosmic voids. While the universe contains dense regions, galaxies, stars, planets, it also contains vast voids, regions hundreds of millions of light years across containing very few galaxies. These voids aren't completely empty. They contain dark matter, dark energy, and occasionally small isolated galaxies. But they're remarkably empty compared to galactic filaments and clusters. The voids form the universe's large-scale structure, a cosmic web where galaxies cluster along filaments surrounding empty bubbles, creating foam-like architecture on the largest observable scales. The structure formed through gravitational attraction, matter gravitating toward regions of slightly higher density in the early universe, leaving behind regions of lower density that expanded into voids. The voids are expanding faster than the universe's average expansion rate because they contain less matter to slow expansion through gravitational attraction. This creates the universe's accelerating expansion. As voids grow and dominate more volume, their rapid expansion pulls the cosmic average expansion rate upward. The voids thus drive cosmic destiny, their emptiness more consequential than the matter between them. Consider for a moment what happens at the edge of the solar system. The sun's influence doesn't end abruptly. It gradually diminishes with distance. The solar wind, a stream of charged particles emanating from the sun, extends outward, creating a bubble called the heliosphere that protects the inner solar system from interstellar radiation. This bubble extends roughly 11 billion miles from the sun, beyond Pluto's orbit, where it encounters the interstellar medium, the sparse gas, dust, and cosmic rays that fill the space between stars. The boundary where solar wind meets interstellar medium is called the heliopause, a dynamic, constantly fluctuating region where two environments collide. The Voyager spacecraft crossed this boundary in 2012 and 2018, becoming humanity's first objects to enter interstellar space. Beyond the heliopause lies true interstellar space, unimaginably empty, incredibly cold, bathed in cosmic radiation, utterly hostile to life as we know it. The distance between our sun and the nearest star could contain 6,600 solar systems placed side by side. This vast emptiness means that interstellar travel, even to the nearest stars, would take tens of thousands of years with current technology, making the stars seem reachable yet functionally inaccessible within human lifespans. This reveals something profound about temperature. Space is often described as cold, and it is. Temperatures in interstellar space average around 3 Kelvin, just 3 degrees above absolute zero, the coldest possible temperature where molecular motion nearly ceases. But temperature in space is complicated because there's almost nothing there to be hot or cold. Temperature measures the kinetic energy of particles, their movement and vibration. But in the vacuum of space, there are so few particles that temperature becomes almost meaningless. An object in space doesn't get cold from touching cold surroundings because there's nothing to touch. Instead, objects in space lose heat through radiation, infrared light emitted from their surface, and they gain heat from absorbing radiation, primarily from stars. In direct sunlight near Earth, an object's sunlit side might reach hundreds of degrees above freezing, while its shaded side plummets far below zero. The temperature difference between light and shadow is extreme because there's no atmosphere to distribute heat. This is why spacecraft require careful thermal management, why spacesuits are engineering marvels, maintaining stable temperature in conditions fluctuating by hundreds of degrees. Space is cold in the sense that you would quickly freeze there, but hot in the sense that there's nowhere for your body heat to go except through radiation, which happens slowly, meaning you wouldn't freeze instantly as movies suggest. You'd suffocate first from lack of oxygen. And alongside this, there's something extraordinary about what you'd experience in space. Without protection, the human body is adapted to Earth's atmospheric pressure. 14.7 pounds per square inch at sea level, pressing on every surface of your body. In space's vacuum, that pressure vanishes, creating severe consequences. Your blood wouldn't boil despite space's low temperature. Blood pressure is sufficient to prevent boiling, but water on your tongue, in your eyes, and in your nose would vaporize immediately, causing rapid swelling. Your body wouldn't explode. Skin is strong enough to hold you together, but you would swell significantly as water in tissues vaporized. The air in your lungs would expand, potentially causing lung damage if you didn't exhale immediately. You would lose consciousness within 15 seconds as oxygen-depleted blood reached your brain. Without oxygen, brain damage would occur within a few minutes and you'd be dead within 2 minutes. But the death wouldn't be from freezing or boiling or exploding. It would be from asphyxiation, the same death you'd experience if you stopped breathing on Earth, just with additional injuries from pressure differential and radiation exposure. Survivors of brief vacuum exposure, accidental depressurizations in altitude chambers or spacesuit tests, report that it's not painful, just strange. A moment of confusion followed by unconsciousness. But there's more to the hazards of space. Beyond vacuum, space is filled with radiation. Cosmic rays from distant supernovae, solar radiation from our sun, and high-energy particles streaming through the cosmos. Earth's atmosphere and magnetic field protect us from most of this radiation, but in space, there's no such protection. Astronauts on the International Space Station experience radiation levels roughly 10 times higher than on Earth's surface, accumulating exposure that increases cancer risk. On longer missions, to Mars, for instance, radiation becomes a major concern. A round-trip Mars mission would expose astronauts to radiation equivalent to receiving full-body CT scans every few days for months, significantly increasing lifetime cancer risk. Some cosmic rays are so energetic, they can pass straight through spacecraft and human bodies, breaking apart molecules, damaging DNA, potentially causing genetic mutations. Astronauts report seeing flashes of light when their eyes are closed, cosmic rays passing through their retinas, creating false signals interpreted as visual flashes. This is what space does to unprotected biology. It bombards it with high-energy particles that break molecular bonds, damage cellular machinery, and gradually degrade biological function. Long-term space travel requires either improved shielding, which adds weight, making missions more expensive, or accepting health risks that would be unacceptable in most other contexts, which connects to something deeper about time itself. Time in space doesn't flow the same way it does on Earth. Einstein's relativity revealed that time is relative. It passes at different rates, depending on relative motion and gravitational field strength. Time moves more slowly in stronger gravitational fields, and for objects moving at high speeds, relative to observers. GPS satellites orbiting Earth experience both effects. They're in weaker gravitational field than Earth's surface, making their clocks run faster, but they're moving at high speed, making their clocks run slower. The net effect fact is that satellite clocks run slightly faster than clocks on Earth's surface, and GPS calculations must account for these relativistic effects to provide accurate positions. For astronauts on the International Space Station, time passes fractionally faster than for people on Earth because they're in slightly weaker gravitational field. Though the difference is tiny, microseconds over months, but near massive objects like neutron stars or black holes, time dilation becomes extreme. Near a black hole's event horizon, time slows dramatically relative to distant observers. Someone falling into a black hole would experience time normally, but to outside observers, they would appear to freeze at the event horizon, their watch running slower and slower, asymptotically approaching zero as they neared the horizon. This isn't illusion, it's actual time distortion, a fundamental feature of how space-time works. And here's where it gets even more interesting. The universe itself has aged at different rates in different places. Regions of space near massive galaxy clusters have experienced less time since the Big Bang than regions in voids far from massive objects, because time runs slower in strong gravitational fields. The difference is small, on the order of millions of years across cosmic history, but real. This means the universe doesn't have a single universal age, but rather a range of ages, depending on location and gravitational environment. When we say the universe is 13.8 billion years old, we mean that much time has elapsed in our reference frame. But other locations in space-time have experienced different durations. The universe's age is thus context-dependent, varying by location, making cosmic time more complex than simple linear progression. This temporal variation connects to space's geometry. Regions that have experienced more time have had more time to expand, creating subtle correlations between time elapsed and spatial structure. The universe is thus four-dimensional fabric where time and space interweave, neither independent of the other, both shaped by mass, energy, and expansion. This connects to something remarkable about gravitational waves. Einstein predicted that accelerating masses create ripples in space-time that propagate at light speed, gravitational waves. For decades, these remained theoretical curiosities, but in 2015, the LIGO detectors directly observed gravitational waves for the first time, confirming their existence and opening a new window onto the universe. The detected waves came from two black holes orbiting each other at increasingly high speeds, eventually merging in a collision that released more energy in a fraction of a second than all the stars in the observable universe combined. This energy radiated as gravitational waves, literal ripples in space-time itself, that traveled across 1 billion light-years, reaching Earth and causing LIGO's detectors to measure a change in distance smaller than a proton's width. The detection confirmed that space-time is physical, that it can vibrate like a drumhead, that massive objects don't just move through space but fundamentally alter its structure. Since 2015, dozens of gravitational wave events have been detected. Black hole mergers, neutron star collisions, events releasing gravitational energy that shook the fabric of the universe. Each detection teaches us about extreme physics, about how matter and energy behave under conditions impossible to recreate on Earth, about the universe's violent past and dynamic present. But there's more to space's strangeness. The universe is expanding, but it's not expanding into anything. This is perhaps the most difficult concept to grasp. Expansion without an outside. The universe isn't growing like a balloon inflating into a room. Rather, space itself is becoming more space, distances between distant objects increasing while the objects themselves remain stationary relative to the space immediately around them. Imagine an infinite grid where the spacing between grid lines increases uniformly. Every distance stretches, but there's no edge, no outside, no container. This is how cosmologists understand universal expansion. The expansion is occurring everywhere simultaneously. Space between galaxies is expanding, though the effect is negligible on small scales, where gravity and other forces hold objects together. Only on scales larger than galaxy clusters does expansion dominate, pulling distant galaxies apart. The expansion rate, called the Hubble constant, indicates that space is expanding at roughly 45 miles per second per megaparsec, meaning that for every 3.26 million light-years of distance, recession velocity increases by 45 miles per second. At sufficient distances, recession velocity exceeds light speed, not because objects are moving faster than light through space, but because space itself is expanding faster than light can cross it. This creates a cosmic horizon. Objects beyond this horizon are moving away so fast their light will never reach us, making them permanently unobservable no matter how long we wait. And alongside this, there's something extraordinary about the cosmic microwave background. Shortly after the Big Bang, the universe was hot and dense, a plasma of hydrogen nuclei, electrons, and photons, so energetic that atoms couldn't form. As the universe expanded and cooled, approximately 380,000 years after the Big Bang, it reached a temperature where electrons could bind to nuclei, forming neutral hydrogen atoms. This recombination suddenly made the universe transparent. Photons that had been constantly scattering off free electrons could suddenly travel freely through space. The universe was filled with glowing gas at about 3,000 Kelvin, and the light from this moment has been traveling through space ever since. But because the universe has been expanding, that light has been stretched, red-shifted, from visible orange glow to microwave radiation. This cosmic microwave background now fills the universe at a temperature of 2.725 Kelvin, just barely above absolute zero. It's the oldest light in the universe, a snapshot of conditions 380,000 years after the Big Bang, carrying information about the early universe's temperature, density variations, and composition. Measuring this radiation with extreme precision revealed tiny temperature fluctuations, variations of about 1 part in 100,000, that represent density differences in the early universe. These density variations were seeds of structure. Regions of slightly higher density gravitationally attracted more matter, eventually forming galaxies, stars, and planets. Every structure in the universe today, including Earth, including you, formed from density fluctuations visible in the cosmic microwave background, making it not just ancient light but the blueprint of cosmic structure. Consider for a moment what lies beyond the observable universe. If the universe is infinite, then beyond our cosmic horizon lies infinite space containing infinite galaxies, infinite stars, infinite planets. In an infinite universe, every possible arrangement of matter occurs not just once, but infinitely many times, meaning that somewhere, infinitely far away, there might be exact copies of Earth, of you, living lives identical or different in infinite variations. This is unsettling and perhaps meaningless. We can never interact with these distant regions, never observe them, never confirm their existence. They might as well not exist from our perspective. But if the universe is infinite, they must exist, raising questions about identity, uniqueness, and meaning. Are you special if infinite copies exist? Does your life matter if infinite versions play out every possibility? These are philosophical rather than scientific questions, but they arise naturally from cosmology's implications. Alternatively, the universe might be finite but unbounded, curved back on itself like a sphere's surface, where traveling far enough in one direction eventually returns you to your starting point. A finite universe avoids the infinite copies problem, but raises others. What lies beyond a finite universe? How big is it? The questions have no clear answers, just models and speculation extending beyond what observation can confirm. This reveals something profound about our place in the cosmos. Earth orbits an average star in an unremarkable spiral galaxy, itself part of a small galaxy group, in a relatively empty region of the universe. There's nothing special about our location, no center, no privileged position. The Copernican principle holds that we don't occupy a special place, that the universe looks roughly the same from any vantage point, that our observations represent typical cosmic conditions. This principle has guided cosmology successfully, but it's also humbling. We're not at the center, not unique, not positioned to see anything other observers elsewhere wouldn't see. Our corner of the universe is representative, our observations generalizable. But this means we're profoundly average in cosmic terms. The universe doesn't revolve around us, doesn't care about us, proceeds according to physical laws indifferent to human existence. This perspective shift, from thinking Earth is the center to recognizing our ordinariness, represents one of humanity's great philosophical transitions, enabled by astronomy and space exploration. Understanding our cosmic insignificance is strangely liberating. We're not burdened with cosmic importance, not required to fulfill universal purpose. We're free to create our own meaning in a universe that provides none. And as you settle deeper now, imagine floating in space, surrounded by stars in every direction, no up or down, no left or right, just infinite depth extending forever. The stars aren't twinkling, that's an atmospheric effect. They're steady points of light, some white, some red, some blue, each one a nuclear furnace converting mass to energy through fusion, pouring light into the void. Behind the stars, barely visible, the Milky Way stretches across the sky. A river of light that you finally understand is edge-on view of the galaxy's disk. Billions of stars so distant they blur together into glowing band. And beyond everything, barely perceptible, the faint glow of distant galaxies, some spiral like ours, some elliptical, some irregular, each containing billions of stars, many hosting planets, some of those planets perhaps harboring life that looks up at their sky and wonders, just as we do, whether anyone else is out there. The silence is total. Space carries no sound, no vibration, no medium for pressure waves. There's only light, arriving after journeys lasting seconds or millennia, carrying information about distant times and places, telling stories of cosmic events no human witnessed but that we can reconstruct from photons captured by our instruments. This is space, vast, empty, beautiful, hostile, indifferent, eternal. This is the reality beyond atmosphere, the universe as it actually exists when you strip away the comfortable filter of Earth's protective envelope. The speed of light isn't just fast. It's the universe's ultimate speed limit, embedded into space-time's structure itself. Nothing with mass can reach light speed, because doing so would require infinite energy. As objects accelerate, they gain relativistic mass, requiring ever more energy to accelerate further, approaching, but never reaching light speed. Light itself travels at this speed, not because photons are trying to go fast, but because they're massless. Particles without mass naturally move at light speed through vacuum, unable to move any slower. This speed limit creates the universe's communication barrier. Information cannot propagate faster than light, meaning events separated by large distances cannot influence each other instantaneously. When the sun suddenly disappeared, Earth would continue orbiting for 8 minutes, the time light takes to cross the distance, before gravitational changes propagated to us. The speed limit also means that causality is preserved. Cause always precedes effect in all reference frames. Without this limit, time travel paradoxes could occur, allowing effects to precede causes, breaking fundamental logical consistency. The universe's structure depends on this speed limit, making it not arbitrary constant but necessary feature of reality, which brings us to understand why space is so empty. After the Big Bang, matter and energy expanded into growing volume. As space expanded, the density of matter decreased. The same amount of stuff spread across. More space means lower concentration. Early universe was dense, but 13.8 billion years of expansion has diluted matter until space is now extraordinarily empty. The average density of the observable universe is approximately 6 hydrogen atoms per cubic meter. Basically nothing. Even within galaxies, where matter concentrates, most volume is empty space. The solar system consists almost entirely of vacuum with tiny specks of matter, planets, asteroids, dust, scattered within it. Even solid matter is mostly empty. Atoms are tiny nuclei surrounded by electron clouds, and the nucleus occupies only about 1/4 of the atom's volume. If an atom were scaled to the size of a sports stadium, the nucleus would be a marble at the center, and the electrons would be tiny particles orbiting near the outer walls, with vast emptiness in between. This means everything, you, Earth, stars, is mostly empty space, just with electromagnetic forces creating the illusion of solidity. The universe's emptiness isn't a bug, but a feature, a consequence of expansion and the fundamental structure of matter. And this connects to something remarkable about interstellar dust. While space is mostly empty, it's not completely empty. There's dust, gas, and plasma scattered throughout, especially within galaxies. Interstellar dust consists of tiny particles, carbon, silicates, ice, some only nanometers across, others as large as micrometers. These dust grains block and scatter starlight, creating dark patches visible in the Milky Way and other galaxies. The dust also glows faintly in infrared light, warmed by starlight it absorbs. This dust is crucial for star formation. Cold gas clouds containing dust can collapse under gravity to form stars, with dust providing sites where molecules can form, and helping clouds cool by radiating energy away. The dust also affects observations. It dims and reddens distant stars, effects astronomers must correct for when measuring distances and brightnesses. The dust originated in dying stars, red giants shedding outer layers, supernovae exploding, creating atoms heavier than hydrogen and helium, and expelling them into space. Over billions of years, successive generations of stars have enriched interstellar space with heavier elements, creating dust that will form future stars and planets. This cosmic recycling means that all solid matter, planets, asteroids, your body, consists of elements created in stars and expelled as dust, making us not just figuratively, but literally children of stars. But there's more to the space between stars. Interstellar gas, primarily hydrogen and helium, fills the gaps between dust grains. Most of this gas is neutral atomic hydrogen, single hydrogen atoms drifting through space. This hydrogen emits faint radio waves at 21-centimeter wavelength, the emission line astronomers use to map the galaxy's structure and measure rotation. Other regions contain ionized hydrogen, hydrogen atoms stripped of electrons by ultraviolet light from nearby hot stars. These HII regions glow pink in visible light, creating spectacular nebulae visible through telescopes. Still other regions contain molecular hydrogen, H2 molecules, the densest, coldest parts of interstellar space where stars are actively forming. These molecular clouds are huge, hundreds of light years across, and contain enough mass to form thousands or millions of stars. The Orion Nebula, visible to naked eye as fuzzy patch in Orion's sword, is one such region, a stellar nursery where stars are being born right now, their light illuminating surrounding gas and dust. Interstellar space thus contains multiple phases of matter in various states: cold molecular clouds, warm neutral medium, hot ionized gas, each occupying different volumes and playing different roles in galactic ecology. This leads to something equally fascinating about magnetic fields in space. Space isn't just permeated by matter and radiation, but also by magnetic fields threading through galaxies and intergalactic space. These fields are incredibly weak by everyday standards, millions of times weaker than Earth's magnetic field, but they extend across vast volumes, making them cosmologically significant. The fields affect charged particles, causing them to spiral along field lines rather than moving in straight paths. Cosmic rays, high-energy particles streaming through space, are deflected by these magnetic fields, taking wandering paths through the galaxy rather than traveling directly from sources to Earth. The magnetic fields also affect star formation. They provide pressure that helps support gas clouds against gravitational collapse, regulating the rate at which stars form. The fields can also be amplified. Collapsing gas clouds compress field lines, increasing field strength, creating conditions where magnetic pressure becomes significant. Some of the most magnetized objects in the universe are neutron stars, particularly magnetars. Neutron stars with magnetic fields trillions of times stronger than Earth's, so intense they distort atomic structure and create extreme conditions found nowhere else. The magnetism pervading space demonstrates that electromagnetic forces, while weaker than gravity on cosmic scales, still play crucial roles in structuring the universe. Consider for a moment the neutrinos streaming through space and through you. Neutrinos are nearly massless particles that barely interact with matter. They can pass through light years of lead without being stopped. They're produced in enormous numbers by nuclear reactions in stars, by supernovae, by cosmic ray collisions, by the Big Bang itself. Trillions of neutrinos pass through your body every second, almost all of them traveling straight through without interacting with a single atom. The sun produces neutrinos in its core through fusion reactions, and these neutrinos reach Earth in 8 minutes, the time light takes, because they escape the sun's interior almost immediately, unlike light, which takes tens of thousands of years to random walk from core to surface. Detecting neutrinos requires massive detectors buried deep underground to shield from other particles. Experiments like IceCube at the South Pole, which uses a cubic kilometer of Antarctic ice as detector, observing faint flashes of light when rare neutrino interactions occur. Neutrino astronomy provides unique information. Neutrinos come directly from sources without absorption or deflection, carrying information about conditions in stellar cores, supernova interiors, and other extreme environments inaccessible to light. The neutrinos flooding space are ghosts, passing through matter as if it doesn't exist, connecting us to nuclear processes in distant stars, carrying energy and information across the cosmos. And alongside this, there's something extraordinary about the cosmic ray bombardment. Space is filled with cosmic rays, atomic nuclei and subatomic particles accelerated to near light speed by supernovae, black holes, and other violent events. These particles carry enormous energy. Some exceed energies achievable in particle accelerators by factors of millions. And when they strike Earth's atmosphere, they create cascades of secondary particles that rain down to the surface. Cosmic rays affect electronics. They can cause computer errors, flip bits in memory, create spurious signals in detectors. The atmosphere shields Earth's surface from most cosmic rays, but at high altitudes and in space, the flux is much higher. Astronauts experience cosmic ray hits regularly. Those flashes of light they see with closed eyes are cosmic rays passing through their retinas. Over time, cosmic ray exposure causes cumulative damage, increased cancer risk, potential neurological effects, accelerated aging. The highest energy cosmic rays, called ultra-high energy cosmic rays, are so energetic that their origins remain mysterious. They seem to come from beyond our galaxy, but their energies are so high they shouldn't be able to reach us from distances greater than about 160 million light-years because they'd lose energy interacting with the cosmic microwave background. Yet we detect them, implying either unknown nearby sources or exotic physics we don't understand. Cosmic rays demonstrate that space isn't empty, but filled with high-energy particles moving at relativistic speeds, creating radiation environment that life must shield against to survive, which connects to the way the solar wind shapes space around planets. The sun constantly emits charged particles, protons and electrons, that stream outward through the solar system at speeds of 250 to 750 miles per second. This solar wind carries the sun's magnetic field with it, creating the heliosphere. When the solar wind encounters planets, interactions depend on whether planets have magnetic fields. Earth's magnetic field deflects solar wind, creating a protective bubble, the magnetosphere, that shields the surface from charged particles. The interaction creates beautiful auroras, northern and southern lights, when particles that do penetrate the field collide with atmospheric molecules, causing them to glow. Mars lacks a global magnetic field, so solar wind directly impacts its atmosphere, gradually stripping it away over billions of years. This atmospheric loss likely transformed Mars from a warmer, wetter world with thick atmosphere into the cold, dry desert we see today. Venus also lacks intrinsic magnetic field, but its thick atmosphere creates its own magnetic barrier. Jupiter has immensely strong magnetic field, 20,000 times stronger than Earth's, creating magnetosphere so large it would appear larger than the full moon if visible to human eyes from Earth. The interaction between solar wind and planetary magnetic fields structures space around planets, creating complex electromagnetic environments that affect spacecraft, satellites, and any future human presence beyond Earth. But there's more to solar activity than steady wind. The sun occasionally releases massive bursts of plasma and magnetic field in events called coronal mass ejections. These CMEs hurl billions of tons of material into space at millions of miles per hour. When directed toward Earth, they can cause geomagnetic storms, disturbances in Earth's magnetic field that induce currents in power grids, disrupt satellite operations, and create spectacular auroras at unusually low latitudes. The 1859 Carrington event, the strongest geomagnetic storm in recorded history, caused telegraph systems to fail, shocked operators, and created auroras visible near the equator. If a similar event occurred today, it could damage power transformers, disable satellites, disrupt GPS and communications, and cause widespread technological failures, costing trillions of dollars. Scientists monitor solar activity to predict space weather, issuing warnings when CMEs head toward Earth so operators can protect infrastructure. The sun's variability demonstrates that space isn't static, but dynamic. The environment between planets constantly changes, buffeted by solar activity that waxes and wanes on time scales, from minutes to decades. Living and working in space means adapting to this variability, protecting against radiation storms, and accepting that space is more hostile than our everyday Earth experience prepares us for. This reveals something profound about exoplanets, planets orbiting other stars. For centuries, humans wondered whether other stars had planets, but detecting them was technologically impossible. In 1995, the first confirmed exoplanet around a sun-like star was discovered, opening a new field of astronomy. Since then, thousands of exoplanets have been confirmed, with many thousands more candidates awaiting verification. The discoveries reveal that planets are common. Most stars have planets, suggesting billions of planets in our galaxy alone. The planets discovered show enormous diversity: hot Jupiters, gas giants orbiting extremely close to their stars, super-Earths, rocky planets larger than Earth but smaller than Neptune, ice giants, ocean worlds, lava planets. Some orbit in their star's habitable zone, the range of distances where liquid water could exist on the surface, making them potentially habitable. Discovering life on exoplanets remains beyond current capabilities, but future telescopes will analyze exoplanet atmospheres, searching for biosignatures, chemical combinations unlikely to persist without life. Finding even microbial life elsewhere would revolutionize our understanding, proving life arises wherever conditions permit, suggesting the universe might teem with life we haven't detected yet. Conversely, finding no life despite extensive searching might suggest life is extraordinarily rare, making Earth precious beyond measure. Either answer would profoundly affect how we understand our place in the cosmos. And here's where the search becomes deeply personal. The Drake equation attempts to estimate the number of communicative civilizations in the galaxy by multiplying factors: star formation rate, fraction of stars with planets, number of habitable planets per star system, fraction where life develops, fraction where intelligent life evolves, fraction that developed detectable technology, and average lifetime of technological civilizations. Most factors are uncertain. We don't know how likely life is to begin, how often intelligence evolves, how long civilizations survive. Optimistic estimates suggest thousands or millions of civilizations in the galaxy. Pessimistic estimates suggest we're alone. The Fermi paradox asks, if intelligent life is common, where is everyone? Why haven't we detected signals, observed megastructures, or been visited? Possible answers range from cheerful, civilizations are common, but use communication methods we don't recognize, to ominous, civilizations inevitably self-destruct before achieving interstellar contact. The Great Filter hypothesis suggests there's at least one extremely improbable step in the evolution of intelligent life. If the filter is behind us, life's origin perhaps, or the evolution of complex cells, then we're rare but survivors. If the filter is ahead, perhaps technological civilizations always destroy themselves, then our future is bleak. The silence of the cosmos might be the most significant observation we've made, teaching us something profound about life, intelligence, or our own future. This connects to something deeper about time scales. The universe is 13.8 billion years old, an incomprehensible duration. Earth is 4.5 billion years old, about a third of the universe's age. Modern humans have existed for about 300,000 years, a blink in cosmic time. Recorded human history spans about 5,000 years, barely visible on geological time scales. Our entire technological civilization, radio, spaceflight, computers, exists for only about a century. On cosmic time scales, humanity appeared an instant ago and might vanish an instant hence. If civilizations typically survive only brief periods, centuries, or millennia, then even if intelligent life is common, civilizations might rarely exist simultaneously at distances allowing communication. Two civilizations separated by thousands of light years might both exist. But if each exists for only a few centuries, the chances they overlap temporally become small. Add light speed communication delay, messages taking millennia to arrive, and meaningful exchange becomes impossible even if civilizations overlap. The universe might be full of civilizations that existed, exist, or will exist, but temporal and spatial separation prevents contact, leaving each civilization alone in practical terms, even if not statistically rare. Time's vastness creates isolation as profound as space's vastness. Consider for a moment what happens when galaxies collide. Despite containing hundreds of billions of stars, galaxies are mostly empty space, meaning when galaxies collide, stars almost never collide. They pass between each other like interpenetrating clouds. But the gas in galaxies does collide, creating shockwaves that compress gas clouds and trigger vigorous star formation. Galaxy collisions thus create starburst galaxies, systems producing stars hundreds of times faster than normal, blazing brilliantly for millions of years before exhausting available gas. The Milky Way and Andromeda galaxies are approaching each other at about 250,000 miles per hour and will collide in roughly 4.5 billion years. The collision will take hundreds of millions of years. Galaxies will pass through each other, swing back, merge into single larger, elliptical galaxy. The Sun and Earth will likely survive unscathed, though they'll be flung to a different location in the merged galaxy. The collision will dramatically alter the night sky for any observers on Earth. Andromeda will grow larger, eventually filling much of the sky. Then both galaxies will distort into tidal streams before settling into new configuration. Galaxy collisions are common in universe's history. Most galaxies have experienced multiple mergers, acquiring mass and transforming structure through cosmic cannibalism. Our galaxy contains remnants of smaller galaxies it consumed, their stars now orbiting as part of the Milky Way, ghosts of extinct galaxies whose individual identities were erased by gravitational mixing. And alongside this, there's something extraordinary about gravitational lensing. Massive objects bend space-time, and light following space-time's curves appears to bend around massive objects, an effect called gravitational lensing. When massive galaxy or galaxy cluster lies between Earth and more distant object, the cluster's gravity bends light from the distant object, potentially creating multiple images, arcs, or complete rings called Einstein rings. Gravitational lensing allows astronomers to study objects too distant to see otherwise. The lensing brightens and magnifies background objects, revealing galaxies from early universe that would otherwise be undetectable. Lensing also reveals dark matter's distribution. Observing how light is bent reveals the mass distribution of the lensing object, including dark matter which doesn't emit light, but still gravitationally lenses background sources. Some of the most beautiful astronomical images show galaxy clusters with dozens of lensed background galaxies, creating arcs and distortions throughout the field. Visual demonstrations of spacetime's curvature, evidence that gravity is geometric rather than force in traditional sense. Gravitational lensing turns massive structures into natural telescopes, magnifying the distant universe and allowing observations impossible with telescopes alone. This reveals something profound about dark matter. Observations of galaxy rotation, gravitational lensing, cosmic microwave background, and large-scale structure all indicate that the universe contains far more matter than we can see. The visible matter, stars, gas, dust, comprises only about 5% of the universe's total mass energy. Roughly 27% is dark matter, matter that doesn't emit, absorb, or reflect light, but exerts gravitational influence. We detect dark matter only through its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than visible matter suggests. Gravitational lensing reveals more mass than we see. Dark matter's nature remains unknown. It might consist of weakly interacting massive particles, axions, primordial black holes, or something else entirely. Despite decades of searching, direct detection remains elusive. Dark matter apparently doesn't interact electromagnetically. No light, no electric charge, interacting only gravitationally and possibly through weak nuclear force. The dark matter forms scaffolding upon which visible matter gravitates. Dark matter's distribution determines where galaxies form, how they evolve, how structure grows across cosmic history. Without dark matter, galaxies wouldn't have enough mass to hold together, galaxy clusters wouldn't exist, and the cosmic structure we observe couldn't have formed. Dark matter is thus an essential component of reality, despite remaining invisible and mysterious, which brings us to understand dark energy, even stranger than dark matter. In the 1990s, observations of distant supernovae revealed that the universe's expansion is accelerating. Galaxies are moving apart faster now than in the past. This acceleration requires repulsive force, counteracting gravity, something pushing space apart. Cosmologists call this dark energy, comprising about 68% of the universe's total mass energy. Dark energy's nature is completely unknown. It might be cosmological constant, a property of space itself where empty space has inherent energy causing expansion. It might be quintessence, a dynamic field that varies in time and space. It might indicate that gravity works differently on cosmic scales than Einstein predicted. Dark energy's effects become dominant only on the largest scales and at late cosmic times. Early universe was matter-dominated, with gravity slowing expansion. But as universe expanded and matter diluted, dark energy's constant or slowly varying contribution became relatively more important, eventually dominating and causing acceleration. Dark energy will determine the universe's ultimate fate. If it remains constant, expansion will continue accelerating forever, eventually tearing apart galaxy clusters, then galaxies, then stars, then atoms in a big rip. If dark energy decays, expansion might decelerate or even reverse, potentially leading to Big Crunch, where universe collapses back to singularity. The universe's far future depends on dark energy's properties, which remain profoundly mysterious despite being the dominant component of reality. And as you drift deeper into this contemplation, consider that approximately 95% of the universe consists of dark matter and dark energy, substances we've never directly detected, don't understand, and know about only through their gravitational effects. The universe you see, stars, galaxies, planets, all the light and matter, represents only 5% of reality. The rest is dark, invisible, mysterious, known only through mathematics and indirect observation. This suggests that human perception is extraordinarily limited, that reality vastly exceeds what we can directly observe, that the universe might be stranger than we imagine, or perhaps stranger than we can imagine. The humble recognition that we don't understand most of reality, despite centuries of scientific progress, despite powerful instruments, despite brilliant minds working on these problems, should inspire both wonder and humility. We've learned enough to recognize how much we don't know, mapped enough of reality to see the vast, uncharted territories remaining. The universe keeps secrets, maintains mysteries, resists full comprehension. Perhaps some questions have no answers we can discover. Perhaps reality's deepest truths lie forever beyond human reach. Or perhaps future generations will solve mysteries we can't, will understand what we don't, will look back at our ignorance with the same bemusement we feel reading about ancient cosmologies. Either way, tonight, this moment, we float in space. Some of it visible, most of it dark, surrounded by mysteries, living in universe we barely understand, searching for answers that might not exist. The cosmic web, the large-scale structure of the universe, resembles neural networks or biological systems more than random distribution. Galaxies cluster along filaments surrounding vast voids, creating patterns that look eerily similar to brain cells connected by synaptic networks or to mycelium spreading through soil. This similarity isn't coincidental, but arises from mathematical principles governing how networks form under certain constraints. Gravity attracts matter to regions of slightly higher density, creating filaments that grow and intersect at nodes where galaxy clusters form. The resulting structure maximizes connectivity while minimizing energy, the same optimization that shapes neural networks, river systems, and countless other natural phenomena. The cosmic web contains filaments stretching hundreds of millions of light years, connecting galaxy clusters in a vast scaffolding that emerged from tiny density fluctuations in the early universe. Mapping this structure reveals the universe's skeleton, the underlying architecture upon which all visible structure hangs. The web is dynamic, constantly evolving as gravity pulls matter along filaments toward nodes, as dark energy accelerates expansion between structures, as the universe ages and its architecture gradually transforms. We live within one strand of this web, in a galaxy situated on a filament, surrounded by voids, connected through gravity to structures extending across observable space. Which brings us to understand what black holes actually are. A black hole isn't an object, but a region of space-time curved so severely that escape becomes impossible beyond a boundary called the event horizon. Inside the horizon, all paths lead inward. Space itself is falling into the singularity faster than light can travel outward. Anything crossing the event horizon is lost to the outside universe forever, unable to send signals, unable to escape, destined to reach the central singularity where space-time curvature becomes infinite and known. Physics breaks down. Black holes form when massive stars exhaust nuclear fuel and collapse. If the stellar core remaining after supernova exceeds about 3 solar masses, no known force can prevent gravitational collapse to a black hole. Smaller stellar remnants become neutron stars or white dwarfs, held up by quantum mechanical pressure. But beyond a critical mass, even quantum pressure fails, and collapse continues until a singularity forms. Supermassive black holes, millions to billions of solar masses, lurk at the centers of most galaxies, including ours. The Milky Way's central black hole, Sagittarius A star, contains about 4 million solar masses compressed into a region smaller than Mercury's orbit. How supermassive black holes formed remains uncertain. They might have grown from stellar mass black holes that merged and accreted matter over billions of years, or they might have formed directly in the early universe from collapsing gas clouds. Black holes aren't cosmic vacuum cleaners. They don't suck in surrounding matter any more than a star of equivalent mass would. Objects can orbit black holes safely just as planets orbit stars. Only material that ventures too close, inside the event horizon or into accretion disk orbits, gets captured. And this connects to something remarkable about what happens near black holes. As you approach a black hole's event horizon, gravitational gradients become extreme. The difference in gravitational pull between your feet and head, if falling feet first, would stretch you into long, thin strand, in process called spaghettification. For stellar mass black holes, this tidal force becomes lethal far outside the event horizon, tearing apart any object before it crosses the boundary. But for supermassive black holes, the event horizon is so large that tidal forces at the horizon remain relatively gentle. You could cross the horizon without immediately noticing, though you'd be doomed regardless, unable to escape, and destined to reach the singularity within minutes or hours, depending on the black hole's size. Time dilation. Near black holes is extreme. An observer far from the black hole watching something fall in would see it slow as it approaches the horizon, appearing to freeze just outside, its clock running slower and slower, light red shifting until it becomes undetectable. But the falling observer experiences nothing unusual. Time passes normally. They cross the horizon in finite time, then inevitably reach the singularity. This is relativity's strangest prediction. The same event looks utterly different to different observers, neither perspective more correct than the other, both valid in their reference frames. The black hole interior is a place where space and time swap roles. Inside the horizon, moving forward in time means moving toward the singularity, just as inevitably as outside the horizon, moving forward in time means moving toward the future. You can no more avoid the singularity once inside than you can avoid tomorrow. But there's more to black holes than destruction. Hawking radiation, predicted by Stephen Hawking in 1974, but never directly observed, suggests black holes aren't perfectly black, but emit faint thermal radiation due to quantum effects near the event horizon. Virtual particle pairs constantly form in empty space, normally annihilating almost immediately, but near the event horizon, one particle can fall in, while the other escapes, appearing as radiation emanating from the black hole. This radiation carries energy away from the black hole, causing it to lose mass, black hole evaporation. For stellar mass or larger black holes, evaporation is negligibly slow, taking vastly longer than the current age of the universe. But smaller black holes evaporate faster, and very small black holes would evaporate explosively. Hawking radiation implies black holes aren't eternal, but slowly decay, eventually disappearing in final burst of radiation. This creates the black hole information paradox. Quantum mechanics requires information to be preserved, but if black holes evaporate completely, information about what fell in seems to be destroyed, violating fundamental physical principles. Whether information is truly lost, encoded in subtle correlations in the radiation, or preserved in some other way, remains one of theoretical physics's deepest unsolved problems, lying at the intersection of quantum mechanics and general relativity, where both theories struggle and might need modification. This leads to something equally fascinating about quasars. In the early universe, some galaxies contain actively feeding supermassive black holes surrounded by bright accretion disks, swirling maelstroms of gas spiraling inward, heated to millions of degrees by friction and gravitational compression, radiating enormous energy across all wavelengths. These active galactic nuclei, particularly the brightest variety called quasars, outshine their entire host galaxies, pouring out more energy than hundreds of normal galaxies combined from regions smaller than solar systems. Quasars are the most luminous persistent objects in the universe, visible across billions of light years, beacons marking locations of massive black holes, feeding voraciously during their host galaxy's youth. The quasar era peaked roughly 10 billion years ago, when the universe was younger and gas-rich, providing ample fuel for black hole growth. Today, quasars are rare. Most supermassive black holes are dormant or feeding slowly, producing little radiation. Our own galaxy's central black hole is currently quiet, accreting material at a trickle, producing almost no luminosity. But evidence suggests it was more active in the past, and could become active again if disturbed material falls inward. Quasars demonstrate that black holes, despite their simplicity, characterized by just mass, spin, and charge, can create spectacular phenomena, regulating galaxy evolution by heating gas and preventing star formation, shaping their cosmic environments despite being infinitesimally small compared to galaxies they inhabit. Consider for a moment neutron stars, the universe's densest objects except for black holes. When massive stars collapse in supernovae, if the remaining core is between about 1.4 and 3 solar masses, it becomes a neutron star, matter compressed until electrons are forced into protons, creating neutrons, producing object composed almost entirely of neutrons, packed together as densely as atomic nuclei. A neutron star, the mass of the Sun, would be only about 12 miles in diameter, city-sized object containing more mass than our Sun. A sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. The surface gravity is about 200 billion times stronger than Earth's, strong enough that dropping an object from 1 meter height would cause it to hit the surface at millions of miles per hour. The magnetic fields of neutron stars, especially magnetars, reach intensities trillions of times stronger than any magnetic field humans can create, strong enough to distort atomic electron orbitals and make vacuum itself birefringent. Neutron stars rotate rapidly, some spin hundreds of times per second, creating pulsars that sweep beams of radiation across space like cosmic lighthouses. The physics inside neutron stars remains uncertain. At such extreme densities, matter might form exotic states like quark matter or superfluids, conditions impossible to recreate in laboratories and difficult to model theoretically. Neutron stars are laboratories for extreme physics, testing matter's behavior under conditions that push the boundaries of known science. And alongside this, there's something extraordinary about what happens when neutron stars collide. When binary neutron stars orbit each other, they gradually spiral inward, losing energy to gravitational waves, eventually colliding in events called kilonovae. The collision produces multiple phenomena simultaneously: gravitational waves rippling through space-time, gamma-ray bursts of enormous energy, and heavy element nucleosynthesis. The extreme conditions during collision, temperatures of billions of degrees, densities rivaling atomic nuclei, create neutron-rich environments where rapid neutron capture produces heavy elements beyond iron. Gold, platinum, uranium, and other heavy elements in the universe, including in your jewelry and in Earth's crust, were likely produced in neutron star collisions. In August 2017, gravitational wave detectors and telescopes observed a neutron star collision, the first multi-messenger astronomy event, where gravitational waves and electromagnetic radiation from the same event were detected simultaneously. The observations confirm that neutron star collisions produce heavy elements, that they create gamma-ray bursts, and that they might be the primary source of the universe's gold and platinum. The collision also resolved debates about whether such events produce black holes or temporarily stable hypermassive neutron stars. In this case, a black hole formed, surrounded by debris that produced optical, infrared, and radio emission over subsequent weeks. Neutron star collisions are rare, but spectacular events that shape cosmic chemical evolution and demonstrate the violent beauty of extreme physics, which connects to the cosmic distance ladder, how astronomers measure distances to faraway objects. For nearby objects, parallax works. Observing apparent position shifts as Earth orbits the Sun allows trigonometric distance calculations. For more distant objects beyond parallax range, astronomers use standard candles, objects whose intrinsic brightness is known, allowing distance calculation from observed brightness. Cepheid variable stars, stars whose brightness varies periodically in ways related to their intrinsic luminosity, serve as standard candles for nearby galaxies. Type 1 supernovae, exploding white dwarfs with fairly consistent peak brightness, serve as standard candles for more distant galaxies. For the most distant objects, Hubble's law relates recession velocity to distance, allowing distance estimation from redshift measurements. But each rung of the distance ladder depends on previous rungs. Errors compound, uncertainties accumulate. The cosmic distance scale remains one of astronomy's persistent challenges. Different measurement methods sometimes give inconsistent results, creating tensions like the Hubble tension, where local universe measurements of expansion rate disagree with cosmic microwave background measurements by several %. Resolving these tensions might require new physics, or might simply require better measurements and understanding of systematic errors. Distance measurement shapes our understanding of the universe's size, age, expansion rate, and ultimate fate. Getting distances right matters fundamentally. This reveals something profound about redshift. Light from distant galaxies is shifted toward longer wavelengths, redshift, because space itself expands while light travels through it, stretching the light's wavelength along with space. This cosmological redshift differs from Doppler shift caused by motion through space. It's not that galaxies are moving away through static space, but that space between us and them is expanding, carrying galaxies apart. The relationship between redshift and distance enables cosmological studies. Observing redshift tells us how much the universe expanded since light was emitted, which relates to distance and look-back time. The most distant objects observed have redshifts exceeding 10, meaning the universe has expanded more than tenfold since their light was emitted, meaning we see them as they existed more than 13 billion years ago, when the universe was young. Studying high redshift objects reveals early universe conditions, the first galaxies, first stars, conditions shortly after the Big Bang. The James Webb Space Telescope was specifically designed to observe high redshift objects in infrared light. Visible and ultraviolet light from early galaxies has been redshifted into infrared by the time it reaches us, requiring infrared-sensitive instruments to detect. Each increase in observable redshift extends our view backward in time, closer to the Big Bang, revealing earlier chapters of cosmic history. And here's where time becomes strange in cosmic context. The universe's expansion creates temporal complications. What does now mean across cosmic distances? Different reference frames experience time differently, and light-speed communication delay means we can never observe distant objects as they are now, but only as they were when light left them. For extremely distant objects, now becomes meaningless. By the time we see them, billions of years have passed at their location. They've evolved beyond recognition or ceased to exist. The observable universe has cosmic time, proper time, measured by co-moving observers, moving with universe's expansion, allowing meaningful statements about the universe's age. But local time near massive objects, or at high velocities, diverges from cosmic time. The universe is thus temporally complex. Different regions have experienced different durations since the Big Bang, depending on local gravitational fields and motions. The idea of universal simultaneity breaks down. There's no absolute now extending across space, only local simultaneity within limited regions where light speed delays and gravitational time dilation remain negligible. Thinking about cosmic timescales requires abandoning everyday assumptions about time's nature, accepting that time is local, relative, and intimately connected to space's geometry and matter's distribution. But there's more to the early universe than current observations reach. Before recombination, before the universe became transparent and the cosmic microwave background formed, the universe was opaque to light. We can't see earlier times through electromagnetic radiation because photons couldn't travel freely. But gravitational waves from the early universe should be detectable. Space-time distortions created by inflation, phase transitions, or other early events would propagate to the present, potentially observable with sufficiently sensitive detectors. Primordial gravitational waves would carry information about conditions in the first fraction of a second after the Big Bang, testing theories of cosmic inflation and revealing physics at energy scales inaccessible to particle accelerators. Similarly, primordial neutrinos, relics from 1 second after the Big Bang, should fill the universe but have never been directly detected because they're so low energy and interact so weakly. If detected, they would provide snapshot of the universe when it was 1 second old. The early universe remains mostly invisible to us, its conditions inferred indirectly from later effects. Abundances of light elements created in Big Bang nucleosynthesis, temperature fluctuations in the cosmic microwave background, large-scale structure patterns. Each indirect measurement constrains early universe models, but doesn't provide direct observation. The first moments of cosmic history remain mysterious, accessible only through mathematical models and indirect inference. This connects to something deeper about inflation, a hypothetical period when the universe expanded exponentially for a tiny fraction of a second shortly after the Big Bang. inflation was proposed to solve several cosmological puzzles. Why the universe appears so uniform in all directions, despite causally disconnected regions. Why space's curvature is so close to flat. Why certain predicted particles, like magnetic monopoles, aren't observed. Inflation solves these by proposing that a tiny patch of space expanded exponentially, becoming smooth and flat through expansion, with quantum fluctuations in the inflating region, creating tiny density variations that seeded structure formation. After inflation ended, the universe transitioned to slower expansion, proceeding through the familiar Big Bang evolution. Inflation remains unproven. While it elegantly explains observations, alternative models exist, and direct evidence is lacking. The primordial gravitational waves inflation should produce haven't been detected. The field driving inflation, the inflaton field, has never been identified, though many candidates have been proposed. Inflation pushes explanation for the universe's properties back to even earlier, more speculative physics, raising questions about what caused inflation to begin and end, what existed before, whether before even makes sense in this context. The theory is beautiful and empirically successful, but possibly impossible to definitively confirm or falsify. Consider for a moment the possibility of multiverses. If inflation occurred, quantum fluctuations during inflation might have created regions where inflation ended at different times, producing multiple bubble universes within a larger, inflating space. Each bubble universe could have different physical constants, different particle physics, different dimensions, variations on physical law determined by how symmetries broke during inflation's end. Our observable universe would be just one bubble, surrounded by other bubbles we can never observe or interact with because they're beyond our cosmic horizon and receding due to ongoing inflation outside all bubbles. This eternal inflation scenario suggests a multiverse of infinite variety. Some bubbles with physics similar to ours, others utterly different, perhaps unable to support any structure or complexity. If the multiverse is real, it raises the anthropic question: are the physical constants in our universe finely tuned to allow life? Because if they weren't, we wouldn't exist to observe them. This anthropic reasoning is controversial. Some view it as profound insight, others as abandoning scientific explanation. The multiverse hypothesis is possibly untestable. If we can never observe other universes, is the concept scientific? Does it explain anything or merely push mystery back another level? These questions remain unresolved, debated by physicists and philosophers, highlighting tensions between mathematical beauty, empirical verification, and scientific methodology. And alongside this, there's something extraordinary about the universe's fine-tuning. The fundamental constants of nature, strength of gravitational force, electromagnetic force, strong and weak nuclear forces, masses of fundamental particles, cosmological constants value, appear finely tuned to allow existence of complex structure. Alter any constant by small percentage, and atoms couldn't form, stars couldn't fuse heavier elements, chemistry couldn't produce complex molecules, life as we know it couldn't exist. This apparent fine-tuning demands explanation. Is it coincidence, necessity, or design? The multiverse offers one explanation. If infinite universes exist with varying constants, we inevitably find ourselves in one where constants allow observers. Other physicists argue that future theories will show constants are necessarily what they are, that they couldn't have other values. Still others invoke design, that the universe was intentionally configured to support life. None of these explanations is fully satisfying. Multiverse is speculative and possibly untestable. Necessity hasn't been demonstrated and might not exist. Design raises questions about the designer. The fine-tuning question sits at the boundary of physics, philosophy, and metaphysics, unanswerable with current knowledge, perhaps forever beyond scientific resolution. It reminds us that science, despite enormous success, reaches limits. Some questions might not have empirical answers, might require philosophical or even theological frameworks, or might simply be wrong questions reflecting anthropocentric bias. This reveals something profound about entropy and heat death. The second law of thermodynamics states that entropy, disorder, always increases in closed systems. The universe, being everything, is the ultimate closed system, meaning universal entropy increases inexorably. In the far future, this leads to heat death, a state where entropy is maximized, where all usable energy has been converted to waste heat, where stars have burned out, black holes have evaporated, and nothing remains but thin soup of particles at uniform temperature barely above absolute zero. In this state, no energy gradients exist to drive processes, no work can be done, no life can exist. The universe becomes cold, dark, empty, changeless, not destroyed but rendered maximally dull. Heat death won't occur for unimaginably long times. Current estimates suggest 10 to the 100 years or more. But eventually, if current physics is correct, the universe approaches this state. The thought is depressing. Everything we build, everything we accomplish, every structure from atoms to galaxies will eventually disperse into maximum entropy. But it's also distant enough to be irrelevant, practically. Humanity will be long gone. The sun will have burned out. Perhaps the species that succeed us will find solutions or meanings we can't imagine. Heat death represents thermodynamics' ultimate victory, entropy's final claim, the slow winding down of cosmic energy into uniformity and stillness. Which brings us to understand the anthropic principle more carefully. The weak anthropic principle states that we observe the universe to have properties, allowing our existence because if it didn't, we wouldn't be here to observe it. A tautology that's nonetheless true. The strong anthropic principle suggests the universe must have properties, allowing observers to eventually exist. A much more controversial claim implying purpose or teleology. Some physicists embrace anthropic reasoning, others reject it as anti-scientific. The debate centers on whether observer selection affects the fact that we can only observe universes compatible with observers, explain apparent fine-tuning, or merely restate the puzzle without solving it. Anthropic reasoning is most compelling in multiverse scenarios where many universes exist with varying properties. Observer selection naturally explains why we find ourselves in a life-compatible universe without invoking design or necessity. But if only one universe exists, anthropic reasoning offers little explanatory power. It's merely observing that we couldn't exist if conditions were different, which doesn't explain why conditions are as they are. The anthropic principle highlights the strange role of observers in cosmology. We're simultaneously insignificant cosmic specks and necessary components of any complete theory. Because physics without observers is meaningless. Observations define reality in quantum mechanics, and the universe's comprehensibility to minds requires explanation. And as you drift further now, consider that you're floating through space on a planet orbiting a star in a galaxy containing hundreds of billions of stars, in a universe containing trillions of galaxies, most of which we'll never observe, because they're beyond our cosmic horizon, receding faster than light can cross the space between us. You're made of atoms forged in dying stars, arranged into patterns complex enough to be conscious, to wonder, to seek understanding. You exist briefly, decades if fortunate. While the universe exists for billions of years, will continue existing for trillions more, proceeding through eras of structure, then emptiness, then heat, death, all according to laws that might be necessary, or might be one possibility among infinite alternatives in a multiverse we can never observe. Your existence is improbable, temporary, and cosmically insignificant. Yet here you are, conscious and wondering, capable of understanding the universe's vastness and your smallness within it. This understanding is itself remarkable. That matter can organize into patterns that comprehend reality, that the universe can know itself through minds that arise within it. Tonight, you're experiencing a moment of cosmic self-awareness, the universe contemplating itself through you. Matter and energy arranged in configurations that ask questions, seek patterns, build meaning from mathematical structures that might be fundamental reality or might be maps our minds impose on something ineffable beneath. Rest now in this strangeness, this impossible existence, this brief window of consciousness opening onto infinity, knowing that tomorrow the sun will rise, Earth will continue spinning, and space will remain vast, mysterious, beautiful, indifferent, eternal. The vacuum of space holds more energy than all the matter in the universe combined. This vacuum energy, sometimes called zero-point energy, arises from quantum field fluctuations, the seething quantum foam underlying reality. Even in the coldest, emptiest regions of space, quantum fields never truly rest, but oscillate around minimum energy states, creating energy density that permeates all existence. Calculating this vacuum energy density produces absurd results. Naive quantum field theory calculations yield values roughly 10 to the 120 times larger than observations allow, possibly the worst prediction in physics history. Something cancels most of this energy, leaving only the tiny amount we observe as dark energy. Why the cancellation is so precise, why any vacuum energy remains at all, why it has the specific value driving cosmic acceleration. These questions remain completely unanswered. The vacuum energy problem, also called the cosmological constant problem, represents a fundamental disconnect between quantum mechanics and general relativity, suggesting our understanding of reality's deepest level is profoundly incomplete. Space itself might be the universe's deepest mystery, not empty stage, but active participant, filled with energy and structure we barely comprehend, operating according to principles we've glimpsed but not mastered. Which brings us to understand quantum entanglement across cosmic distances. When particles become entangled, their quantum states correlated so that measuring one instantly affects the other regardless of separation. The correlation persists across any distance. Photons from opposite edges of the galaxy could be entangled, their properties correlated, despite light years of separation, no signal passing between them, because entanglement doesn't transmit information, just maintains correlations established when particles interacted. The universe might be filled with entangled particles, creating quantum connections spanning space, linking distant regions in ways classical physics can't describe. Some theorists propose that space-time itself emerges from quantum entanglement, that space is not fundamental but constructed from entanglement relationships between quantum fields, that the geometry we perceive arises from underlying quantum correlations. If true, this would revolutionize physics. Space and time wouldn't be basic ingredients of reality, but emergent phenomena, approximately valid at large scales, but breaking down at quantum scales where entanglement dominates. The universe would be fundamentally non-local, with correlations more basic than spatial relationships, with distance emerging from quantum information structure rather than being primitive feature of reality. And this connects to something remarkable about the holographic principle. Black hole thermodynamics suggests that information content of any region of space is proportional to the region's surface area rather than its volume, as if three-dimensional space is somehow encoded on two-dimensional boundaries. The holographic principle generalizes this, proposing that the entire universe might be described by information encoded on its boundary, that our three-dimensional reality might be a projection of two-dimensional information structure. This seems absurd. We experience three dimensions directly, but mathematics suggests it might be true. String theory's ADS/CFT correspondence demonstrates explicit examples where gravitational theories in higher dimensions are exactly equivalent to quantum theories on lower dimensional boundaries. If the universe is holographic, volume is illusory. The third dimension, not truly independent, but redundant encoding of boundary information. We'd be living in something like a cosmic hologram, projections of information existing elsewhere, experiencing three dimensions despite reality being fundamentally two-dimensional. The holographic principle remains speculative and controversial, but it addresses deep questions about quantum gravity, black hole information, and space-time's nature, suggesting reality might be stranger than we imagine. But there's more to space's quantum nature. At the Planck scale, roughly 10 to the negative 35th meters, the smallest meaningful length in physics, space itself becomes quantum mechanical, fluctuating and uncertain. At these scales, space-time geometry isn't smooth but foamy, seething with quantum fluctuations, creating constantly shifting configurations of microscopic wormholes, tiny black holes forming and evaporating, space-time itself becoming probabilistic rather than definite. We can't observe Planck-scale physics directly. Building accelerators powerful enough would require planet-sized machines. But theoretical physics suggests space-time's smooth geometry is approximate description, valid only at scales much larger than the Planck length. Quantum gravity, the theory unifying quantum mechanics with general relativity, must describe this quantum space-time, must explain how smooth classical space-time emerges from quantum foam, must resolve singularities like black hole centers where classical theory predicts infinite curvature. String theory, loop quantum gravity, and other quantum gravity approaches propose different pictures of Planck-scale structure, but none is empirically verified. None makes predictions testable with current technology. Quantum space-time remains theoretical frontier, where physics reaches limits of current understanding, where speculation exceeds confirmation, where nature guards secrets possibly forever beyond human reach. This leads to something equally fascinating about wormholes, hypothetical shortcuts through space-time connecting distant locations. General relativity allows wormhole solutions, curved space-time geometries containing tunnels linking different regions. If wormholes exist and are traversable, they would enable faster-than-light travel without actually moving faster than light. You'd travel through ordinary space at ordinary velocities, but the wormhole's geometry would make the journey shorter. However, calculations suggest that traversable wormholes require exotic matter with negative energy density. something that probably doesn't exist in large quantities or might be impossible. Even if wormholes could be constructed, they'd likely be unstable, collapsing before anything could traverse them, or they might allow closed time-like curves, paths through space-time that return to their starting point before they began, enabling time travel and creating paradoxes. Most physicists doubt traversable wormholes exist naturally or can be artificially created, but they can't definitively rule them out. Wormholes remain speculative possibility, theoretically permitted by known physics, but practically impossible, highlighting the gap between what equations allow and what reality contains. Consider for a moment the cosmic coincidence problem. Why do dark energy and dark matter have roughly similar densities today, when throughout most of cosmic history, they had vastly different densities? Early universe was radiation-dominated, then matter-dominated for billions of years, then dark energy dominated as expansion accelerated. These transitions happened at specific times, determined by how densities evolve. Radiation dilutes faster than matter, which dilutes faster than dark energy. By coincidence, we exist during the brief cosmic era when dark matter and dark energy have comparable densities, when neither completely dominates. In the past, dark energy was negligible. In the future, it will dominate overwhelmingly. Why now? This seems suspiciously anthropic. Perhaps observers can only exist during this brief window when structure formation occurred, but before dark energy rips structures apart. Or perhaps it's purely coincidental, an unremarkable accident given that someone must exist sometime, and whenever they exist feels special to them. Or perhaps dark energy is dynamical, its density tracking matter density for reasons we don't understand, solving the coincidence through new physics. The cosmic coincidence problem illustrates how observations sometimes reveal puzzles rather than answers, how understanding breeds new mysteries, how the universe consistently surprises us. And alongside this, there's something extraordinary about the measurement problem in cosmology. Quantum mechanics requires measurement to collapse wave functions, turning quantum superpositions into definite outcomes. But the early universe had no observers, nothing conscious, nothing that could measure. How did the universe's wave function collapse? How did quantum fluctuations during inflation become classical density perturbations, seeding structure formation? Decoherence, quantum states losing coherence through interaction with environment, provides partial answer, explaining how superpositions become effectively classical without requiring conscious observers. But interpretational questions remain. Did the universe exist in superposition until the first observers evolved? Does the past become definite retroactively through present observations? Does quantum mechanics apply to the universe as a whole, or only to subsystems within it? These questions probe the boundary between physics and philosophy, between empirical science and interpretive frameworks. Cosmology forces confrontation with quantum measurement problem in contexts where ignoring interpretation isn't possible. We must decide what quantum mechanics means when applied to everything, not just laboratory systems. The answers shape how we understand reality's nature. Whether observers are fundamental or incidental, whether physics is complete or requires consciousness as additional ingredient. This reveals something profound about the arrow of time. Physical laws are mostly time symmetric. Equations work equally well forward or backward in time, yet we experience time flowing forward, never backward. Past is fixed and knowable through records. Future is open and unknowable beyond statistical prediction. This temporal asymmetry arises from thermodynamics. Entropy increases forward in time, creating direction. Low entropy past, concentrated energy, organized structure, evolved into higher entropy present, will evolve into even higher entropy future. But why was the past low entropy? Why did the universe begin in organized state rather than maximum entropy? This boundary condition, low entropy Big Bang, remains unexplained. Perhaps inflation set up low entropy initial conditions. Perhaps the Big Bang wasn't truly initial. Preceding events prepared special starting configuration. Perhaps asking why requires answer beyond physics, involving selection effects or anthropic reasoning. Only low entropy beginnings produce observers wondering about entropy. The arrow of time's origin remains mysterious, connecting to the universe's beginning, to thermodynamics' deepest principles, to the nature of causation and temporal experience. Why time flows forward is perhaps the most basic question we can ask, yet it remains incompletely answered, which connects to cosmic inflation's arrow. During inflation, the universe's entropy increased enormously as space expanded exponentially. This seems to violate the principle that early universe had low entropy. Inflation was high entropy process. The resolution involves recognizing that entropy depends on what you count. Inflation increased entropy of matter and radiation while keeping gravitational entropy low. Space remained smooth and flat rather than collapsing into black holes, which represent gravitational systems' maximum entropy. After inflation, gravitational entropy continued increasing as matter clumped under gravity, forming stars, galaxies, clusters, and eventually black holes. The universe's total entropy increases throughout history, with different contributions dominating at different eras. The ultimate high entropy state might be universe filled with evaporated black holes, remnant radiation, maximally dispersed and thermalized. This progression from smooth early universe to clumpy, present to dispersed future represents entropy's relentless increase, thermodynamics playing out on cosmic stage, driving cosmic evolution from Big Bang to heat death across trillions of years. But there's more to time's cosmic nature. The universe's age differs depending on reference frame and location. In regions with strong gravitational fields, time passes more slowly, so less time has elapsed since the Big Bang. In rapidly moving reference frames, time dilation means less time experienced. The universe thus doesn't have single age but range of ages, depending on where and how you measure. When cosmologists say the universe is 13.8 billion years old, they mean that much time has elapsed in the reference frame of observers, moving with the universe's expansion, co-moving observers. But near massive objects, or in different reference frames, elapsed time differs. The concept of cosmic time, a shared time coordinate for the universe, is approximate, valid only for co-moving observers far from massive objects. Precise descriptions require specifying reference frame and location. Time's relativity applies cosmologically. The universe's history is frame-dependent, cosmic chronology is observer-dependent, and universal simultaneity doesn't exist. This reinforces that time is not absolute, but intertwined with space, observer-dependent, relative rather than universal. The universe has no objective age, independent of how it's measured. This connects to something deeper about the Big Bang singularity. General relativity predicts that extrapolating backward in time leads to a moment when the universe had infinite density and temperature, a singularity where physics breaks down. But singularities usually indicate where theories fail, rather than what reality does. Quantum mechanics should matter at such extreme conditions, preventing true infinities. Quantum gravity, whatever its correct formulation, should replace the classical Big Bang singularity with something more physical. Perhaps a quantum bounce where the universe contracted, then expanded. Perhaps a fuzzy quantum region where space and time become uncertain. Perhaps something we can't currently imagine. The Big Bang wasn't an explosion in space, but space itself beginning to exist, or transitioning from some prior state. Whether time existed before the Big Bang, whether before is meaningful, whether the universe's origin is physical event or mathematical boundary, remains unknown. The singularity reminds us that physics doesn't explain everything, that extrapolating to extremes leads to places where current theories fail, that the universe's deepest secrets, its origin, its fundamental nature, its ultimate fate, might lie forever beyond complete comprehension. Consider for a moment how alone we are in this cosmos. Humanity exists on one planet orbiting one star in one galaxy, in a universe containing trillions of galaxies. We've achieved consciousness, developed science, built technology, explored our local environment, but we remain confined to Earth, barely beginning to reach nearby space, decades from reaching another planet, centuries from reaching another star, millennia from reaching another galaxy. We search for signals from other civilizations, broadcast messages hoping someone might receive them eventually, but receive only silence. Perhaps we're alone, the only conscious observers in the observable universe, the only minds comprehending cosmic vastness, the only species asking these questions. Or perhaps intelligence is common but fragile, emerging then self-destructing before achieving interstellar communication. Or perhaps civilizations exist but are so different we don't recognize their signals, or communicate using methods we haven't imagined, or deliberately hide from detection, or exist at times or places that prevent contact. We might be cosmically isolated not through uniqueness, but through space-time's vastness. Other civilizations exist, but are too far away, too separated in time, too different in nature for contact to occur. The silence might be temporary. Perhaps we'll detect signals eventually, make contact, learn we're part of cosmic community. Or the silence might be permanent, teaching us that consciousness is rare, precious, isolated, that we're truly alone, responsible for being the universe's only eyes, only minds, only hope for understanding. And alongside this, there's something extraordinary about the future of space exploration. Humanity dreams of becoming spacefaring civilization, establishing bases on Moon and Mars, mining asteroids, building habitats throughout the solar system, eventually reaching other stars. But space is brutally hostile. Vacuum, radiation, extreme temperatures, vast distances, absence of resources. Every mission requires enormous investment. Every astronaut faces significant health risks. Every habitat must be completely self-sufficient because resupply from Earth is expensive and slow. Establishing permanent presence in space requires solving formidable engineering challenges, creating closed-loop life support, generating power from solar panels or nuclear reactors, shielding from radiation, manufacturing supplies from local materials, maintaining equipment that can't be easily repaired. Even if technically feasible, economic and political will might be lacking. Space colonization doesn't obviously benefit Earth. Costs are immense, returns uncertain. Humans might remain confined to Earth, not through physical impossibility, but through practical difficulty and lack of compelling reason to leave. Alternatively, perhaps artificial intelligence or modified humans, enhanced to survive radiation, tolerate low pressure, endure isolation, will colonize space while baseline humans remain on Earth. The future might see humanity split, Earthbound biological humans and space-adapted post-human descendants, or AI, diverging evolutionarily or technologically, eventually becoming different species or civilizations. This reveals something profound about our cosmic responsibility. If we're alone, or functionally alone due to isolation, then consciousness might be exceedingly rare. Earth might host the only minds in our cosmic neighborhood, perhaps in the observable universe. This makes humanity's survival cosmically significant. If we destroy ourselves, consciousness might disappear from vast regions of space for billions of years or forever. Our arts, sciences, philosophies, compassion, love, all products of consciousness, might be universe's only such products. Conversely, if intelligence is common, our responsibility diminishes. Other minds exist, other civilizations achieve understanding, and our existence or extinction affects only our local region. We don't know which scenario is true. Whether we're rare and precious or common and replaceable, this uncertainty should inspire both humility and caution. Humility because we might be cosmically ordinary. Caution because we might be extraordinary. Either way, our existence is remarkable. We're patterns of matter that experience, understand, create meaning. Whether alone or accompanied by countless others, consciousness is valuable. Understanding is worthwhile. Creating beauty and knowledge and compassion matters regardless of cosmic context. Which brings us to understand that you are made of space. The atoms composing your body are mostly empty. Electrons orbiting nuclei at distances vastly larger than nuclear size, creating illusion of solidity from electromagnetic forces, preventing atoms from interpenetrating. But even this empty space isn't truly empty. It's filled with quantum fields, virtual particles, vacuum energy. You're not separate from space, but continuous with it. Your boundaries, arbitrary divisions in continuous field of matter and energy extending throughout the universe. The atoms in your body were once scattered across interstellar space, gathered into molecular clouds, collapsed into stars, forged into heavier elements, expelled in supernovae, drifted through space again, eventually incorporated into the solar nebula that formed Earth, weathered into soil, absorbed by plants, eaten by animals, eventually becoming you. Those atoms will eventually return to space. After your death, decomposition, geological cycling, eventual solar expansion, vaporizing Earth, dispersing atoms back into cosmos, where they might someday become part of other worlds, other beings, continuing eternal cycle of matter through space and time. Your temporary organization of stardust, brief pattern in cosmic flow, momentary consciousness arising from matter's endless rearrangement. And here's what this reveals about perspective. From human viewpoint, you're important. You have dreams, relationships, experiences, goals, meaning. From cosmic viewpoint, you're irrelevant. One organism among trillions on one planet among trillions, existing briefly in vast universe, affecting nothing beyond your immediate environment. Both perspectives are true simultaneously. The cosmic perspective doesn't negate the human perspective. Your life matters to you, to those who love you, to the small sphere of influence you affect. Meaning is local and subjective, not cosmic and objective. The universe doesn't care about us, but we care about each other, and that's sufficient. We create meaning through consciousness, relationships, understanding, creativity. Not by appealing to cosmic significance, but by being what we are, experiencing what we experience, valuing what we value. Space's vastness contextualizes human life, revealing our smallness, but doesn't diminish our significance, because significance is internal quality, not cosmic judgment. We're simultaneously insignificant and infinitely valuable. Insignificant cosmically, valuable personally. Holding both truths together is wisdom, neither inflating human importance through anthropocentrism, nor dissolving it through nihilism, but accepting paradox that we're both nothing and everything, depending on perspective. This connects to something deeper about wonder. Learning about space, its vastness, strangeness, beauty, hostility, can evoke profound wonder, the emotional experience of encountering something far greater than ourselves, something beautiful and terrible and incomprehensible. Wonder is response to sublime, to experiences that simultaneously attract and overwhelm, that produce pleasure and fear, that make us feel small yet connected to something vast. The night sky naturally evokes wonder. Looking up at stars, contemplating cosmic distances and time scales, recognizing our place in unimaginably large universe. Science enhances this wonder rather than destroying it. Learning that stars are nuclear furnaces billions of miles away, that light reaching our eyes began its journey centuries or millennia ago, that galaxies collide and black holes merge, and space-time curves doesn't reduce wonder, but deepens it, adding layers of understanding to direct experience. The universe is more wonderful than we knew, filled with dark matter and dark energy, permeated by quantum fields, expanding into no outside, containing trillions of galaxies each with billions of stars. Knowledge reveals depths of mystery, not final answers, but deeper questions. Not closure, but opening into ever vaster realms of discovery. Wonder is appropriate response to reality. Not childish awe, but mature recognition of universe's genuine magnificence. And as you release completely into sleep now, let your consciousness expand to encompass what we've explored. The vast emptiness between stars, the violent births and deaths of stellar bodies, the slow expansion of space itself, carrying everything apart, the dark components we can't see, composing most of reality, the quantum foam underlying smooth space-time, the black holes and neutron stars and quasars blazing across the cosmos, the cosmic web of galactic filaments surrounding vast voids, the ancient light from universe's youth still arriving after billions of years of travel. All of this exists, continues existing, will exist long after you and everyone you know has returned to stardust. The universe proceeds according to physical laws, indifferent to human concerns, yet somehow producing conditions, allowing consciousness to emerge, allowing you to exist, to wonder, to understand partially what you're part of. This is the gift and burden of consciousness, awareness of our place in cosmos, recognition of our smallness and temporariness, yet also capacity to understand, to appreciate, to find meaning despite cosmic indifference. Tonight, as you sleep, Earth continues its ancient orbit. The sun continues converting hydrogen to helium in its core. The galaxy slowly rotates. Other galaxies recede into cosmic distances. Space expands. Dark energy accelerates that expansion, and the universe proceeds through its slow evolution from Big Bang to eventual heat death trillions of years hence. You're part of this, not separate observer, but participant, made of the same matter, governed by the same laws, subject to the same forces. Your consciousness is universe's consciousness, matter arranged in patterns that experience and understand, cosmos knowing itself through you, through every conscious being, wherever they exist, in space and time. This is simultaneously humbling and exalting. You're nothing special, just physics. Yet physics somehow produces awareness, and that awareness can comprehend physics, creating strange loop where universe studies itself through structures it created. Sleep now, knowing that space continues, vast, cold, beautiful, mysterious, filled with wonders we've barely begun to discover, with questions we've barely begun to ask, with phenomena we haven't imagined. Tomorrow you'll wake on your planet, under your star, in your galaxy, and space will still be there, always has been, always will be, backdrop and context for everything, container and creator, nothing and everything simultaneously. Rest in this knowledge, rest in this vastness, rest knowing that you're made of space and stars, that your cosmos looking at itself, that your existence, however brief and small, participates in something ancient and vast and ongoing. The universe is stranger and more beautiful than we can fully comprehend, and you're part of that strangeness and beauty. If this journey through space has expanded your sense of wonder, if you'd like to explore more mysteries together in the nights to come, I'd be grateful if you'd subscribe. There are infinite subjects waiting to be discovered, infinite facts that can carry us gently towards sleep, while expanding our understanding of this extraordinary reality we briefly inhabit. Good night. Rest well. The stars will still be there tomorrow.